Assalamu alaikum. Let's start lecture 5 of CS 218 Data Structures and Algorithms. In the last lecture, we arranged functions in order of their growth rates. We realized that algorithms with slower growth rates are better than algorithms with faster growth rates. We learned that the coefficients can be ignored in asymptotic analysis. And we agreed that for fast execution, we need better algorithms more than we need faster machines. We continue with analysis of algorithms and use chapter 4 of book 1 and chapter 2 of book 2. Let me introduce you to asymptotic notations. When we look at input sizes large enough to make only the order of growth of the running time relevant, we are studying the asymptotic efficiency of algorithms. Asymptotic analysis is typically analysis of algorithms for large input sizes. The following notations have been defined for asymptotic analysis: big O notation, big omega notation, big theta notation, little o notation, and little omega notation. Big O notation. Given functions fn and gn, we say that fn is OGN if there are positive constants c and n naught such that fn is less than or equal to cgn for n greater than equal to n naught. Look at the picture. I have got one function called fn. I have got another function called c times gn. And as you can see, when we start from very small values of n, fn has a higher value than c times gn. Then it takes a dip and goes down, and then it goes high again. But there is a point on the x-axis marked as n naught, after which the value of fn is always smaller than the value of cgn. N naught is not necessarily the point where the two curves cross. N naught can be any point on the x-axis after which the relationship fn is less than equal to cgn holds till infinity. Whatever happens before n naught, we are not concerned with that. We just want our relation to hold after n naught till infinity. Or you can say that n naught is the smallest integer for which our relation fn is less than cgn holds. N naught is an integer and it has to be greater than 0. Because what is n? N is the input size. If you put 0 data items into an algorithm, it will take 0 time. Actually, it will not execute. So it makes no sense to have the value of n equal to 0. So this means that the value of n has to be greater than 0. That is, the smallest possible value of n naught is 1. And what is c? C is a constant, it is a real number, and it also has to be greater than 0. You can see in this picture that after n naught, fn is always smaller than cgn. In other words, I can say that gn is always higher in value than fn, or gn runs on top of fn. O notation provides an upper bound on running time of an algorithm. Actually, O notation provides me a function which is higher in growth rate than my function fn. We have this question. Find Gn such that Fn is OGn. Fn is 8n plus 5. We need to prove Fn is less than or equal to Cgn. So I need a function Gn which would satisfy this relation for a particular value of C and n naught. We know that 8n plus 5 is less than or equal to 8n plus 5n. In an inequality, if you subtract something from the smaller side, the inequality is not affected. Likewise, if you add something to the larger side, the inequality is not affected. Here, the larger side is the right side, and I have added to the larger side. I have swapped 5 by 5n, and this will hold for all n greater than or equal to 1. In the next step, I add the two terms on the right, and I get this. 8n plus 5 is less than equal to 13n. This is true for all values of n greater than 0. So the smallest possible value of n naught, is 1. Take C to be 13. So Gn is n and Fn is On. The linear function is an upper bound on the growth of Fn. We are saying that the linear function grows faster than Fn. Now, many people would argue that Fn is 8n plus 5 and the function inside the bracket of the O notation is n. How can n grow faster than 8n plus 5? The answer is the O notation is hiding the constant, and the constant is 13. So actually, the faster growing function is not just n. The faster growing function is 13n. The O notation is giving you a function which, when multiplied to a particular constant, will grow faster than your function Fn. This is method 1 to go about this problem. The second method to go about is this. Fn is 8n plus 5. We need to prove that Fn is always less than Cgn. We want a Gn which we can put here and the relation will hold. We know that 8n plus 5 is greater than or equal to 8n plus n. But for this to be true, n will have to be greater than or equal to 5. So I write 8n plus 5 is less than or equal to 8n plus n for all n greater than or equal to 5. And then I can write 8n plus 5 is less than or equal to 9n for all n greater than equal to 5. The smallest possible value of n naught, is 5. Take C to be 9. So Gn is n and Fn is On, and the linear function is an upper bound on the growth of Fn, or the linear function grows faster than Fn. Consider Fn is 3n square plus 4n plus 7, and we need to find the O notation of Fn. We know that 3n square plus 4n plus 7 is less than or equal to 3n square plus 4n square plus 7n square. I have swapped 4n with 4n square and 7 with 7n square on the right side, since the right side is larger and adding to it does not affect the inequality. Now, adding the terms on the right side, I get this. 3n square plus 4n plus 7 is less than or equal to 14n square. This is true for all values of n greater than 0. So the smallest possible value of n is 1. And we take c to be 14, which gives gn to be n square. So fn is O n square. The quadratic function is an upper bound on the growth of fn, or the quadratic function grows faster than fn. Actually, the function that would grow faster than our function would be 14n square. Another function, 3n log n plus 2n. We set out to find its O notation. We know that 3n log n plus 2n is less than or equal to 3n log n plus 2n log n. This time I have swapped 2n with 2n log n. I can add the two terms on the right hand side. This would give me 3n log n plus 2n is less than or equal to 5n log n. For this to work, two things need to be satisfied. N needs to be greater than equal to 1 and log n needs to be greater than equal to 1. But for log n to be greater than equal to 1, n has to be greater than equal to 2. I have two conditions here. If I take n not to be 1, the first condition would be satisfied, but the second would not be satisfied. If I take n not to be 2, both conditions would be satisfied. So I have 3n log n plus 2n is less than equal to 5n log n for all n greater than equal to 2. The smallest possible value of n is 2. C is 5. So Gn is n log n and Fn is O n log n. The logarithmic function is an upper bound on the growth of Fn. Find another pair of C and n naught to satisfy Fn is OGn. Another function is this, 2 raised to n plus n square plus 3. We need to prove Fn is less than equal to C times Gn. We know that 2 raised to n plus n square plus 3 is less than or equal to 2 raised to n plus 2 raised to n plus 2 raised to n. We are making two assumptions here. One assumption is 2 raised to n is greater than or equal to n square. That's why we are replacing it on the larger side. And the other assumption is 2 raised to n is greater than or equal to 3. Now let us first look at the first condition. 2 raised to n is greater than equal to n square. How to solve this for a value of n? Apply log on both sides. Log to the base 2. So on the right side, you can see that n is raised to a power. And by the law of log, this power can get multiplied with the log. On the left side, log and 2 will cancel out. So we get n is greater than or equal to 2 log n. Again, how do you find the value of n? Let's take the help of a table. In this table, for different values of n, I have calculated 2 log n. You can see that n is greater than or equal to 2 log n for the value of 1 and it is greater than or equal to 2 log n for the value of 2, but it is not greater than equal to 2 log n for 3. So this means that this relation holds when n is greater than or equal to 4. Now come to the second assumption. 2 raised to n is greater than equal to 3. Again, apply log on both sides. On the left side, log and 2 will cancel and we will have n is greater than equal to log of 3 to the base 2. The value of log of 3 to the base 2 is this. And from here we can say that n is greater than equal to 2. Now I have two conditions. If I take n to be greater than equal to 2, the first condition would be violated. But if I take n to be greater than equal to 4, both conditions can be easily satisfied. So I have this. 2 raised to n plus n square plus 3 is less than equal to 2 raised to n plus 2 raised to n plus 2 raised to n for all n greater than equal to 4. And then I add all the terms on the right side of the inequality and I get 2 raised to n plus n squared plus 3 is less than equal to 3 times 2 raised to n for all n greater than equal to 4. The smallest possible value of n is 4. C is 3. Gn is 2 raised to n. Fn is O 2 raised to n. The exponential function is an upper bound on the growth of Fn. Point to note. The big O notation of a function is its fastest growing term, disregarding the constants. If Fn is 3 raised to n plus 2n squared plus 3, which is the fastest growing term? 3 raised to n, of course. Fn is O 3 raised to n. See, now you can do it without proving the whole thing. You can just look at a function, find the fastest growing term, and that would be the O notation of the function. For a polynomial function of degree d, which looks like this, Fn is O n raised to d. Why? Because a d n to the power d would be the fastest growing term of this polynomial. The big O notation provides the tightest asymptotic upper bound of Fn. This means that the big O notation gives us a function that is faster than our function and closest to our function. Fn is 5n cubed plus 4n. The geometric and factorial functions have higher rate of growth than Fn. All polynomial functions of degree greater than 3 have higher rate of growth than Fn. So all functions with a higher growth rate can be the big O notation of Fn. That is, Fn is O n factorial. Mathematically, this is correct because n factorial grows faster than Fn. Fn is O a raised to n for all a greater than 1. This is the geometric function and this is mathematically correct too. Fn is O n raised to d for all d greater than 3. This represents polynomials of degree greater than 3. This statement is mathematically correct too. But we need the tightest upper bound, the higher growth rate function that is closest to Fn. Which function would be the most suitable for big O? We know that 5n cube plus 4n will always be less than equal to 5n cube plus 4n cube. Adding the terms on the right, we can say 5n cube plus 4n is less than equal to 9n cube. And from here I can write Fn is On cube. All the statements in red are correct. But when somebody asks you for big O notation, the person is expecting you to give him the function that grows faster than his function and which is closest to his function. So the statement in purple is the correct answer. Asymptotic conventions. 5n squared plus 3n is less than or equal to 8n squared, which means 5n squared plus 3n is O 8n squared. But it is poor taste to mention 8. So 5n squared plus 3n is O n squared. 5n squared plus 3n is less than equal to 8n cubed, which means 5n squared plus 3n is O n cubed. But it is poor taste to use a higher order function for big O notation when a lower order function is available. So 5n squared plus 3n is O n squared. 2n squared is less than or equal to 3n squared plus 4 log n. But it is poor taste to use two terms to describe big O notation and say 2n squared is O 3n squared plus 4 log n whole. Instead, we use a single term that would suffice. So 2n squared is O n squared. Rules for big O notation. If T1n is OFn and T2n is OGn, T1n plus T2n is O of Fn plus Gn, and this is O of maximum of Fn, Gn. If two functions are being added, then the O notation of their sum will be the O notation of the larger function. T1n into T2n is O Fn into Gn. If two functions are being multiplied, then the O notation of their product will be the product of their O notations. Log of n to the base k is On for any constant k. In other words, all logarithmic functions to any base are slower than the linear function. Find the big O notation for the given code fragment. X is 5, Y is 6, Z is X plus Y into 6, then is X greater than 0 and X is less than 100. So if X satisfies both these conditions, done will be true, otherwise done will be false. Rule 1. Lines of constant time. For all code lines that execute in constant time, the big O notation is 1. You can see that all these lines are not inside a loop. They will execute only once, and their execution time will be constant and independent of the value of n or the input size. So the whole code fragment is O1. We define a function x1. Total is 0. We run a for loop till n and we add 1 to total each time. Then we return total. Rule 2. For loops. The running time of a for loop is at most the running time of the statements inside the for loop times the number of iterations. Inside the for loop, the statement is O1. There are n iterations of the for from 0 to n minus 1. So the O notation of the code is 1 into n or On. Another function x2. Count is 0. We run a for with counter variable I from 0 to n minus 1 and increment count every time. Then we run another for with counter variable j from 0 to n minus 1 and increment count every time. Then we return count. Notice that the two fors are not nested inside each other, but they are executing one after the other. When the first for completes execution, then the execution of the second for starts. Rule 3. Consecutive code fragments. The running time of consecutive code fragments is added to give the running time of the entire code segment. So the running time of the first for will be On and the running time of the second for will be On. The running time for count equals to 0 line will be O1. The running time for return count line will be O1. So I have On plus On and the big O notation of the complete code fragment is On. This time the function is x3. Count is initialized to 0. A for loop with variable I goes from 0 to n minus 1. Inside it, a for loop with variable j goes from 0 to n minus 1. Inside the mutual body of both fors, count is incremented every time. When you exit both fors, you return count. Now, the for loop of j is nested inside the for loop of I. Rule 4. Nested loops. The total running time of a statement inside a group of nested loops is the running time of the statement multiplied by the product of the sizes of all the loops. Again, I ignore count equals 0 and return count statements because they are O1. I look at count plus equals 1 statement. This is O1 too, but it is the body of both fors. And each for iterates n times. So I have O1 into n into n. The code fragment is On squared. X4. Count is 0 for I in range n. For j in range 25, count plus equals 1. Return count. I ignore count equals 0 line. This is O1. I ignore return count line. This is O1. I look at the mutual body of the for loops. Count plus equals 1. This is O1. The J for loop runs 25 times, no matter what the value of n. The I for loop runs n times. The inner loop runs a constant number of times. Its iterations are fixed, no matter what the value of n. O 1 into 1 into n. The code fragment is On. X5. Count as 0 for I in range n, for j in range I plus 1. Count plus equals 1. Return count. I ignore the O1 lines like count equals 0 and return count. Count plus equals 1 is the body of both fors. The inner for is different from the previous fors we have seen, because the iterations of the inner for depend upon the value of the counter variable of the outer for. How do we go about this? Let us make a table. When the value of I is 0, the loop of j iterates only once for the value 0, and the number of iterations is 1. When the value of I is 1, j has valid values of 0 and 1. So there are 2 iterations. When the value of I is 2, j goes from 0 to 2. There are 3 iterations. Continuing, the last value of I is n minus 1. For this, the valid values of j are 0 to n minus 1. The number of iterations is n. Here I have listed number of iterations for each value of I. If I want the total number of iterations, I should add the last column of the table. Total number of iterations is 1 plus 2 plus 3, continuing all the way to n. And this can be worked out by the summation formula of an arithmetic series. Total number of terms is n divided by 2. In the bracket, we write the first term and add it with the last term. Now, when you simplify this, you will get n square upon 2 plus n upon 2. And from this expression, I can say that the code fragment is O n squared. The function is now x6. Count equals 0, I equals n. While I is greater than equal to 1, count plus equals 1, I is I divide 2, return count. Count equals 0 is O1, I equals n is O1, return count is O1. Look at the body of the while. Count plus equals 1 is O1, I equals I divide 2 is also O1. Consecutive statements, so O1 plus O1 is O1. I can say that the complexity of the body of the while is O1. I used a new word, complexity. Complexity refers to asymptotic notation. Most of the time it refers to big O notation. So if I ask you the complexity of a function or the complexity of a code fragment, I am talking about the big O notation. So we came to the conclusion that the body of the while is O1. The problem with whiles are we do not know how many times they would iterate. If we knew that, we could multiply the complexity of the body with the number of iterations, and we would have the complexity of the while. We don't know the number of iterations of the while, but we know that the while iterates as long as I is greater than equal to 1. I starts with n. The while loops for these values of I. It starts with n, then it becomes n by 2. In the next iteration, it becomes n by 4. And it keeps on decreasing until in the second last iteration it is 2, and finally it is 1, and then the while loop stops. This sequence of values can also be written like this. N can be written as n divided by 2 to the power 0. N upon 2 can be written as n divided by 2 to the power 1. N upon 4 can be written as n divided by 2 to the power 2. So you can see that every time you can write the value of I as n divided by 2 to some power. This means that I can write the last term 1 as n divided by 2 to the power x, where x is any number. How many values are there in this sequence? You start with n upon 2 to the power 0 and you end at n upon 2 to the power x. There are x plus 1 terms. So the while loop runs x plus 1 times. Now I know the number of iterations of the while, but this is a new variable x, and I have been used to writing big O notations in terms of n. So I need some way to change the x into n, or to represent x as n. Look at the two sequences in front of you. In the first sequence, the last term is 1. In the second sequence, the last term is n upon 2 to the power x. I know that the last terms are the same. So this means that n upon 2 to the power x is 1. And this can be written as 2 to the power x is equal to n. Apply log on both sides of the equation and you get x is log of n. How many times does your while loop run? It runs x plus 1 time. And what is the O notation of the body? 1. So, the O notation of the while is 1 into x plus 1, or O x plus 1. But what is x? X is log n. So, the O notation is O whole log n plus 1. But we always express O notation as a single term. So we will pick the term with the higher growth rate. And the big O notation for the given code fragment will come out to be O log n. Now we have a function x7. Count is 0. For I in range n, count plus equals x6n. Return count. Count equals 0 is an O1 line. Return count is an O1 line. In the body of the for, every time that you enter, you call the x6 function which we saw in the previous slide. How much time does the x6 function take? We just saw that the x6 function is O log n. The for loop goes from 0 to n minus 1. x6n is O log n. The loop iterates n times. So, the O notation of the for is O n into log n, O n log n. This code fragment is linearithmic in complexity. Oh yes, the tasks. You will find a Google form in an assignment in Google Classroom titled Lecture 5 Tasks. I hope that you will be able to answer the questions posed to you after going through this video. So what did we learn today? We learned about the big O notation. We learned how to find big O notation of functions. We learned the rules of the big O notation. And we learned how to find big O notation of code fragments. Things to do. Read the book. Submit your answers to the tasks in this lecture. Note your questions and put them up in the relevant online session. And email suggestions on content or quality of this lecture to me. Take care and Allah Hafiz.